Welcome to the Explainer. Okay, let's dive right into this. Have you ever looked at a massive open world video game or a giant streaming platform and just thought, man, the code behind this must be absolute magic? Well, today we're going to completely shatter that illusion because the logic powering all software, literally all of it, boils down to just three basic super logical rules: loops, conditionals, and state control. That's it. It's not magic at all. It's just really precise instructions. And today we're going to demystify exactly how computers think. To demystify all this, we're going to follow a simple roadmap. We'll hit three main pillars. First up, the repetition engine. Second, hierarchical decision making. And third, environment debugging. Honestly, once you grasp these three things, you've got the underlying logic to understand pretty much any programming language out there. But before we jump into pillar number one, we need a solid anchor, and that anchor is the state variable. A state variable simply stores information about the current condition of a system. Think of it like the computer's memory, keeping track of what's happening right at this exact second. Whether it's your current high score, if your shopping cart is empty, or how many lives you've got left, the state variable tracks it all.
All right, pillar number one, the repetition engine. Specifically, we're looking at the game loop. Now, what's really interesting about this is how computers use loops to pull off rapid, super accurate automation.
See, without loops, a programmer would literally have to type out the exact same instruction millions of times. Nobody has time for that. Instead, a repetition engine does the heavy lifting. Picture one of those classic Mario-style question mark blocks. You hit it over and over and it just keeps spitting out coins, right? Under the hood, that's just a game loop running continuously. It follows a clean set of steps. Step 1. The computer checks a timer condition. Basically, is there time left? If yes, move to step 2. Output a coin. Step 3. Reduce that timer by 1. And then the loop just spins right back to step 1. Check, output, reduce. It repeats this cycle over and over, evaluating the state, taking action, and updating. But here's the catch. A loop can't just run forever. It needs a rule to stop. Visualize the exact moment that hidden countdown timer hits 0. The loop asks its question, is the timer greater than 0? Nope, it hits 0. Instantly, the loop breaks. The coin production completely stops, and that bright flashing block turns a dull gray. This is what we call the stopping condition. The absolutely crucial takeaway here is that the loop keeps running until that controlling state variable changes. Now let's take that exact same video game logic and apply it to something like a Spotify playlist. It's a perfect match. Our game loop said, while the timer is greater than 0, spawn a coin. Our consumer loop says, while the playlist is not empty, play a song. Same logic. It proves that this exact same repetition engine powers the everyday consumer software you use. Whether it's an Amazon cart processing items or a streaming app playing your favorite track sequentially, it all relies on this basic loop logic, just waiting for a specific condition to be met. So let's test this logic out together really quick. Logical challenge number 1. If a block timer starts at 3 and every single hit reduces it by 1, how many times does the loop execute before it terminates? If you traced it out and said 3 times, you totally nailed it. It hits 2, then 1, and the split second it hits 0, bam, loop breaks. Look at that, you're already thinking exactly like a computer evaluates instructions. Okay, let's move right into our second pillar, hierarchical decision making, or as programmers like to call it, nested conditionals. If loops handle the repetition, conditionals handle the intelligence. This is how software adapts its behavior based on its current state using branching decision paths. Let's map this out using a classic video game mushroom power-up. Imagine a branching flowchart. Step 1. A collision occurs between your character and the mushroom. Step 2. The software checks the character's state. And here's where the branch happens. An outer condition asks, is the player currently small? If yes, boom, they follow the branch to grow big. But wait, what if they're already big? Then the software moves to an inner, nested condition, and instead, they score 1,000 points. The final outcome is entirely dictated by the state variable at the precise moment of that collision. Bridging this power-up metaphor to a real-world streaming platform makes this crystal clear. On one side, we have our game branch. If the character is big, give him 1,000 points. On the other side, a streaming branch. If the user is an active subscriber, play the video. Whenever a user requests to play a movie, they have to pass through these identical multi-level security checkpoints. Are they logged in? If yes, nested condition. Are they an active subscriber? If yes, play the video. It strictly evaluates one condition before it even thinks about looking at the next. All right, time for logic challenge number 2. If our character is already big when they hit the mushroom, what happens next? Well,
Because they are already big, the software bypasses that outer condition entirely and rewards 1,000 points. It's all about navigating those branching paths correctly based on whatever the current state is.
You are absolutely mastering this foundational logic. So let's transition into our final pillar, environment debugging, syntax versus logic errors. So the crucial point is understanding the difference between the code editor, the recipe, and the terminal, the actual kitchen. Let's say you're in your code editor typing out instructions. Suddenly, the text cursor starts glaring back at you, maybe glitching out a bit. Why? Because of one tiny, simple formatting mistake. You missed a colon. This is a syntax error. See, computers are incredibly literal. They need absolutely perfect structure. Because of that one missing symbol, the interpreter completely refuses to understand what you're saying. The program never even starts. Execution is stopped dead in its tracks. Now contrast that frozen little syntax glitch with absolute unmitigated chaos. Imagine your terminal, remember, that's the kitchen where the recipe actually gets cooked, completely melting down. It's wildly flooding with endless scrolling text, print coin, print coin, print coin. The code editor isn't frozen here. No, the terminal is stuck in an inescapable infinite loop. This is a logic error. The program is running perfectly fine structurally, but because a stopping condition never flipped to false, it's behaving entirely wrong, just eating up massive amounts of computing power for eternity. Let's break these two bugs down side by side. Does the program start? For a syntax error, nope. For a logic error, yes. Are they easy to detect? Well, syntax errors usually are, right? The computer usually highlights exactly where your typo is. But logic errors, man, they can be incredibly sneaky. Logic errors are way more dangerous because the program is actively running. It's just calculating the wrong math, or picking the wrong branch, or getting stuck in an infinite loop. And it is entirely up to you to figure out why. So how do developers actually regain control of a glitching, frozen terminal? Here is the professional debugging strategy. Step 1. Verify your syntax. Go hunt down those missing brackets or colons. Step 2. Verify your variables. Are your state variables actually storing the data you think they are? Step 3. Trace the execution path. Did the software accidentally take the wrong branch and a nested conditional? And step 4. Verify your loop exit conditions. You absolutely have to ensure your loops have a defined stopping point. Okay, here is your third and final logical challenge. If a loop condition never, ever becomes false, what happens in the terminal? Just connect it directly back to that chaos we saw a second ago. If the stopping condition never triggers, the whole application appears frozen. Your CPU usage absolutely spikes, and the terminal gets flooded with endless scrolling output. That right there is the true danger of a missing exit condition causing an infinite loop. All right, let's bring this all together. Repetition, decisions, and state control build the digital world. And this brilliantly illustrates how the exact same logic that controls a bouncing mushroom or a multi-coin block scales up seamlessly. The same foundation powers massive global data systems, streams movies to millions of homes, and runs complex artificial intelligence. It's all built on the exact same invisible foundation, continuously evaluating state, making decisions, and repeating actions. I want to wrap up this explainer by leaving you with a final thought. Knowing these invisible rules of loops and conditionals, what everyday software are you going to look at differently today? Seriously, the next time you add an item to an online cart or hit play on a song, take a closer look at the interface. See if you can spot the hidden game loops and the branching logic operating right under your fingertips. Thank you so much for joining me for this explainer, and keep exploring the